Supposed to tell you. Okay.
Okay.
Okay, got it. Okay. Can I start?
Yes, you can start.
Yeah. All right. Okay. Hello, everyone. Thank you for coming to this presentation. My name is Cláudio Silva. Today, I'm going to present my work, which is the NDVI Timeseries data processing and validation from the terrain cork oak woodlands. This work was done under the Virtual Mobility Grant of Statistical Cost Actions, and it kind of inserts the theme in the working group too. I have like three contributors: Sofia Sarasoli and João Silva from the Forest Research Center School of Agriculture in the University of Lisbon, and also from Desislava Geneva from the Space Research Center and Technology Institute of Bulgaria Academic Sciences. Okay, so just to start, a quick overview. So I will talk first about some aims and objectives, study sites and equipments, data acquisition and processing, data validation, preliminary results, and discussion. So I just want to stress the fact that I only have preliminary results because this work was developed roughly in 1 month, and I didn't have the time to actually gather the results and have concrete results to show today. So for now, it's going to be only preliminary ones. Okay, so aims and objectives. So the first is the optimization of methodology to obtain phenological indicators of the understory. And the second was the improvement of time series processing and validation of ground-based and satellite sensors, data related to primary productivity. And the two overall objectives was the fitting classification on the three measuring scales, which represents the measuring scales that I'm studying, accordingly with the interpolations and smoothing filters that I have used. And also the validation of trends of time series through goodness of fit and other statistical methods. Okay. So the study site is characterized as a Mediterranean cork oak woodland. It's in Central Portugal, in Coruche, in Machuqueira do Grão property, and at roughly 165 meters of altitude. As you can see in the map, we have a quite heterogeneity, which is characterized of this sort of ecosystems. So the equipment used was field spec 3 AST, spectral radiometer, Decagon SRS spectral reflection sensors. We got these sensors through a grant of the SpecNet, which knowledge over here, and also we data from the satellite, the Landsat, and this data was gathered. So for the field spec, we got the data monthly. Data was gathered in specifically that I'm going to talk today with the herbaceous mixture, where we have 4 plots, and from these 4 plots we got the spectral data, and we derived directly the NDVI. So for the SRS, spectral reflection sensors, we got data 5 in 5 minutes of the understory, as you can see it. This is more or less how it's mounted. So we have one sensors which is hemispherical, which got the radiance, and we have another one which gets the radiance, which was mounted in this case 40 degrees of Nadine North. And from here, we derive the mean NDVI, and we choose from the 11 to 14, because it is when the sun is the most verticality. And so we choose this time frame to derive the mean NDVI. And so for the Landsat, we got this data directly from Besnard and also other contributors, which in the end got this NDVI from the satellite. Okay. So I did some pre-processing, but first of all, I just want to tell you like the time frame that we have for each sensor and for the satellite data. So for the field spec, we have data, as I mentioned before, of the herbaceous mixture from 2011 to 2019. For the SRS spectral reflection sensors, we have the data of the understory from 2015 to 2018. And from the Landsat, we have data from the NDVI from 84 to 2018. So the pre-processing that I did basically was to check the empty data points and numerical values. As you can see here, the data of the herbaceous of the field spec is the one with a greater empty data values, followed by the Landsat over here with 91.3% of NAs, and on the one that have the less empty data points is the SRS. spectral refractance sensor. Then I also went to see the mean empty data points between numerical records, and we have the same pattern as verified on the preprocessing above. Okay, so I got this data from field spec, SRS, and Landsat, and I put it on this software on DATimeS, and I did a bunch of interpolations with it, as you can see here. So most of these interpolations was also done by Bell et al. 2019, which I based most of this work. So I did time span of 1 day. And why 1 day? Because if I would go, for example, 10 days time setting, what the software makes is that it breaks my data in 10 days. So I would have data from day 1, day 10, day 20, and so forth. And that's not what I want. I want to maintain the integrity of all the data. And for that reason, I maintain the time setting of 1 day. So as you can see here, the degree 2 is because when I do this interpolation, it asks me for the degree. And since we are dealing with polynomials, they are from 2nd degree. I also did some smoothing filters, moving average and Stravinsky-Golay, and I did some span, and the span is also related to the smoothing filter and also with theta, but I will talk about this further. Okay, so from here, I divide my work in 2 studies. So the first study is time series data validation, where I basically only did these interpolations on the 3 time series that I already mentioned. And then I did time series trend validation, where on the top of the interpolations, I also did these smoothing filters also. Okay, so let's talk about time series data validation. So basically what I did was like the non-interpolated NDVI time series of each of one of the time series mentioned versus the interpolated NDVI time series. So observed versus estimated. And this was done only for one time series individually, then another time series individually, so you can have a glimpse of it. And what I used to validate the data was the goodness of fit. And basically with the goodness of fit, I based my validation on these 3 parameters in the root mean square error, relative root mean square, and coefficient of variation, which was enough to do the validation. I also did additional calculations, but as I already mentioned, the 3 first were sufficient. Okay. So the preliminary results. So basically, the conventional methods have the best fitting, which was already expected. Okay, the linear is included here, but I should exclude it because it's normal that linear interpolations would have the best fitting of the raw data that we have. So yeah, but the nearest and next and previous and spline were fitting very well. And then we had the machine learning and sigmoid and harmonic algorithms. So I highlighted the polynomial curve fitting because I found it's very useful to observe the overall trend of the NDVI in the time series. So on these plots over here, they are plots generated by DATimeS, and as you can see, the orange line gives us like the overall tendency of the NDVI through a specific time interval. So I think it's quite useful, you know, just to if you need it, just to get like a quick overview of NDVI of your data. Okay, so I also did some improvement suggestions on the DATimeS, and so the first of them was the enable of the application of the interpolation before the smoothing, and why this is important. Okay, so now here I have like this plot. And the green lines are my original data that I have of the NDVI. And the blue lines over here, basically it's the NDVI processed where the interpolations were done first and second were done the smoothing. Whereas on the DATimeS, what they do was that the software, what it does is that it first applies the smoothing filter, in this case, Stravinsky-Golay, and then applies interpolation. What happened here is that we'll have a completely different time series trend compared to the blue one. So in order to, so this is quite important when we're dealing with this type of softwares. So I also did I also propose other improvements, and I think this is like a cool exercise when you're using the software and if you're using for quite a while or you use it intensively, and you can add like some improvements to the developers, which I think in the end would be useful for everyone because everyone could use a more complete software in this case, or a more efficient. Okay, so now jumping to time series trend validation. So again, what I used, just to remember, I used the interpolations I already mentioned before, and smoothing filters. And here is the span that I applied in each of the smoothing filters. Again, the degree of the Slavinsky light was always 2. And this difference that you see here on the span is due to the quantity of NAs. And I'm saying that because, so the understory is the most complete the time series. And what happened is that we can stretch the span days of the smoothing filters, whereas if we do this for the Landsat, which we have a lot of NAs, our data is going to get flat, and that's not what we want. We want to get rid of some noise, noisy, and this is what the smoothing filters does. And so we have to take care as well the fact that if we have a lot of NAs, we cannot stretch a lot the span days on the smoothing filters. So, and what I did here for the time series trend validation was do a linear interpolated herbaceous data versus interpolated but smoothed off understory or Landsat. Okay, just also to point out the thing was that the herbaceous data is the data that have most NAs. As you saw, they have like 97 or 98% of NAs. And that's kind of major fall. But the fact is that this data of the herbaceous, which is the data from the field spec, is the most accurate data that we have. And so this is the data that we're going to use to validate either the SRS understory data time series and the Landsat. Okay, and we use the herbaceous data because in this type of environment in the Mediterranean cork woodlands, the NDVI variations are predominantly justified by the phenological status of herbaceous layer. And so if we got the NDVI of the herbaceous, we have the predominant signal that we need to in order to validate other type of data. And also I had to subset the data to have the same frequencies in order to compare them, of course. Okay, so let's validate the data, but then we have this thing, which is like we have 2 sensors and 1 satellite, and both of them have distinct methodologies for spectral data acquisitions and different NDVI sensitivities. So what happened is that goodness of fit is insufficient. It's insufficient because it measures the discrepancy between the relation of the values. And what we want actually is that we want to look to the trends, because we might have like off values, but the trend could be the same. So what we want to check is that, are we having the same trend? You know, so that's where we start to think about like trend validation. And for that, I included the independent t-test, which verifies the difference between groups, and I focus on the t value and the p value. And I also included the Granger test of causality, which verifies if one time series is useful to predict another one. Just a bit. Okay, so now I'm going to do an exercise with you guys, which is basically what I did to try to validate my data. Okay, so what do we have here? So the black dots represents the data of the field spec of the herbaceous layer, and the black lines, it represents the linear interpolations, and the vertical lines, vertical black lines, it represents the standard deviation. So all these lines, the colorful lines that you see here, basically are data from the understory with different interpolations, which represents the 4 available groups. Okay, so in blue, we have the Fourier 1, the understory of Fourier 1. In red, we have the understory interpolation of the Gauss with the Gaussian regression. Gray, we have next neighborhood, and with the purple, we have the sigmoid. Okay, so we look to this and like, okay, so which of them they have the most similar trend? Okay, so let's look through the statistics over here. Okay, so starting with the t-test, we see that, okay, the p-value is too low. So basically it means that, okay, the slopes of the time series are all significantly different. All right, so but then we can look to the t-value, and the t-value could give us like the trend. And so the lower the t-value, the more close the trend is. And so what we can check here is that, okay, so in the nearest, we have the lowest t-value. Okay, but then we go to the Granger causality test, and what we want is a big F and a lower p-value. And what we see is that the Fourier here, it kind of dominates, if you see it. It kind of dominates with all of the rest. And then we look to the goodness of fit in order to take out some doubts. And then what we see here is that, okay, again, so the Fourier kind of dominates. Okay, we have the same R square, but then the root mean square error is lower in the Fourier. But as you can see already, like we don't like these statistics don't kind of correlate with each other. Well, okay, so now let's look to the same plot, but now with the smoothing filter. As you can see, the theta is a bit more smoothed. I will just put the plot without smoothing and then with the smoothing. Yeah, there you go. And again, let's look to the statistics. Okay, again, like here we see that the nearest have the lowest t-value, but again, the f value of the Granger causality test and the p-value is more suitable on the Fourier, but the goodness of fit also, we see that the sigmoid is a bit lower and also have a higher R square. So we are kind of divided here, like which one we should choose. And so this is also something that I would like to address. And it kind of represents a problem, but also could represent an open door to explore other statistical means. But now I want to show you this example of the Landsat. So again, we have the same interpolations, but the data is different. And also we have here the herbaceous data, the one that will validate our data. Okay, and okay, what I want to show here basically is that in this one with the statistics, kind of the statistics comply now the statistics go right, because here on the Fourier we have the lowest t-value compared to the other ones, we have the highest f, we have the lowest p, we have the lowest error, and we have the higher R square. So here no problem, because all the statistics goes right with the other ones. And the same we can see with the smoothing filters. With the smoothing filters here of the Stravinsky-Golay, the same data, where the statistics really come together and give us and give us that the Fourier is the best fitting compared to the other interpolations. Okay, so now that we passed the exercise, some preliminary results, what we got in the end was that the harmonic algorithms, Fourier 1, 2, and 3, get the best trend fitting with the preliminary research of the results that I had, followed by machine learning regression algorithms with more emphasis to Gaussian progression regression and kernel-rich regression. Also, I want to point out that the smoothing filters really improve the time series trend validation. It might not be clear with this example, this is the previous example that I showed you before, but the truth is that they really improve the trend validation, and we get like a best fitting. And also, this is something that I want to point out, is that the moving average has the great flattening influence than Stravinsky-Golay smoothing filters, which is also nice to acknowledge this. And what I want to show here basically is that, so here on the left, I have the raw data with the linear interpolation. So pure points of data with linear interpolations. And in the blue, we have the data of the Landsat. In red, we have the data of the field spec and their story. And in green, I have the data, no, sorry, the red one of the field spec was the data from the herbaceous layer. And here the green one is the data from the story of the SRS sensors. And then on the right, I basically have the interpolations that I found to have the best trend fitting, and also with a smoothing filter. So in the blue here we have the data of the Landsat with interpolations of Fourier 3 and the Stravinsky-Golay with a span of 15. Whereas in green I have I have interpolations with Fourier 3. The blue one was a Fourier 1, Fourier 3 on green, and with a Stravinsky-Golay smoothing filter of 31 days of span. And yeah, we can see it that we have kind of the better fitting. And also some of these bumps, as you can see, they are in the interval of the standard deviation. Okay, just a quick discussion. So for the time series data validation, we see that goodness of fit is a valuable method to statistics to determine the fittest interpolation, and the DATimeS is the software. The software is a powerful and accessible tool with a great potential for further improvements. For the time series trend validation, things are not so clear, and so some things are useful to discuss over here. So we have the p-value, which is too sensitive, so we cannot use it. But the statistics give us the difference between two time series trends, and here we have how the t-statistics is calculated, and so it could be useful. So I might have to overlook to these t-statistics and explore a bit more about its potential. For the Granger causality test time series, it's like it's not really give us what we want. You know, it could be working another way. It's just because, so in this phrase, I basically try to resume what the Granger causality test does. So if you could follow me, just that. So we have the Landsat NDVI. So it said that it will Granger cause the variable of the field spec if the past values of Landsat help to predict the current levels of the field spec. So we have here a problem because what we want to predict is present values with present values. We don't want to look to the past values of one variable in order to predict the current ones. So here, because we're going to have a lag of data, and that's not what we want because we are plotting data with the same frequencies at the same dates. So that's what we want to look over. So yeah, I might exclude the idea of Granger causality test. Nonetheless, I think it's a good exercise to try to see if one time series could predict another one. And also, as you can see, we have some correlation, but most of the times we have uncorrelations between goodness of fit t-test and Granger causality test. Also because they overlooked of different things. And finally, so future studies would be to apply the t-test and Granger causality test on time series data, which is already validated. So you could have already validated data and try to explore these tests in order to see if they might have some correlation or not, or some correlation that we could create in order to facilitate our trend data validation. And also is that to the search of robust statistical methods to compare trend validation similarity between two distinct time series. And I want to stress this fact because I've been also reading some papers about this concept of trend validation, trend similarity validation of time series. And I don't find so much information of it. And I think it's kind of a useful thing. And also because, why this is important? So because it will improve time series data processing validation and time series trend validation. And lastly, this is also important because on these type of ecosystems that were studied as a Mediterranean cork woodlands, since that they have a high heterogeneity and have a pronounced seasonality and great interannual variability, it's always useful to have ground-based data in order to validate other types of data. But to do that, we have to have like strong statistical methods because empirical methods are always implied. Okay, that's true. But when you have like 20 time series to validate which you have, like from one time series you do like 20 interpolations, and then from those 20 interpolations you want to see which interpolation will be can be validated with one correct time series. And that gets tricky with empirical methods, and so you should apply some statistical ones in order to clear your doubts. Okay, this is some bibliography that I used, and thank you very much for your attention. And if you have some questions or suggestions, I'll be happy to answer them and to have them, that suggestions. Thank you very much.